Okay, good morning to everyone. Assignment is not finished marking yet, so I hope to give you back maybe before Wednesday. But if not, I put out the solution already. So if you can open out your movie, you can see the solution. So you know what to expect for the solution to write. And then I guess we need to decide the replacement date because Hari Raya is either on Friday or Monday. So in either day, we have to do uh, replacement. Okay. Maybe we can decide on the second hour when people are here. Other than that, any question from last week? Question from last week? Okay. If no, then we will start today's lecture. Let's do some recap. Okay, let's do some recap before start. Okay, so for this chapter, we will deal with a concept called primitive root. Okay, so what is primitive root? Well, uh, consider two number such that, okay, so consider a is not zero and is positive such that the GCD is 1. Okay, then what's the primitive root? And so recall that this is a condition you need for your Euler's theorem. Right? So let us define primitive root. Then, okay, let me see. And then let me see. Okay, then A is a primitive root, not n if order of A is phi n. Okay. Okay, still remember what's the order of A means? What's the order of A means? The order of an A means. Or maybe what's the equation that you see in Euler's theorem? Something equals to 1, right? Okay. So, this order means that the least positive integer such that least positive integer x such that a to the x is congruent to 1 mod n. So in this case here, your x here has to be phi n. Do you remember what is phi n? What is phi n? Huh? What function is this? Huh? Euler phi function. So this is calculating what? Number of integer or positive integer less than n that are relatively prime to n, such that okay, relatively prime to. Okay. So you see on one side, it's something that you compose, put together, multiply together, you get one. On the other side, you are counting something different. When you are counting number positive integer, they are relatively prime to n. Okay. Okay, two sides doing different things, though somehow they are the same. I mean, not the same. I mean, get you to something useful. Okay, so what's the usefulness of this primitive root? There's a theorem that we mentioned last time, right? So if you go through the power before phi n, what did you see? Okay, so if r is a primitive root mod n, if you go through all the power of before phi n, then you will form a reduced residue system. Okay. So what's a reduced residue system means again? These are just all the integer that are relatively prime to n. And then Euler phi function will count. How to prove these? Actually, this proof is very easy. Okay, so basically, you want to show that they are all different and they are relatively prime to n. Okay. So first of all, maybe we will see that these powers are relatively prime to n. Sorry. Okay, why? Because we know that r and n are relatively prime. Okay, this is the setup for your primitive root. Okay, we start with something that's relatively prime to n. If you still remember last time how we find primitive root, we just start with a list of relatively prime number, and then we check the power. And then if this is the GCD between two number is 1, what happens if you put more r to it? Definitely it's still 1. Okay? There's no common GCD between r and n, no matter how many times you put r. And then second, to show that they form a complete list here, you just show that they are all different. Okay, because your residue system must have phi n of them, right? And then here are phi n of different things, so it must be everything. Okay, so next thing to show is to show that none of these two are the same. Okay, so again, this is a trick in mathematics. You want to show that these are different. Just pick any two, see whether they are the same or not. Okay, so suppose that maybe any two of them is the same. Okay, then still remember that this is equivalent to saying that the power is the same up to modulo of order of up. Okay, then you just need to check whether their power is the same up to half order of r or not. But then since r is a primitive root, this number here is actually phi n. Okay? It's actually phi n here. So what's next? So what can we do next? I think. Try think about what can we do next. Okay, so I wanted to say that this congruence here actually implies that these two power has to be the same. Why is it true? Uh, Let me think. Usually this is not true, So usually maybe give you some examples. Okay. Let's figure out why is this true. So usually uh, I congruence J, let's say mod something else, and doesn't imply I equals J. Can you think of some example? Can you think of some example? Very easy example. Maybe 2 congruent 6 mod 2, right? But then 2 is not equal to 6. Okay. So when can this be true? When can this be true? When can this be true? Huh? Sorry? When can this be true? And is there any time it can be true? When? Sorry? J is n times. J is 2 times or 3 times of I. You sure? Uh, J is 3 times of. What do you mean by that? Let me think. You mean J? You mean J is 3 times of I like that? No, right? Okay. Well, it can be true when it is exactly the same number, right? For example, I can write like 2 congruence 2 mod 2. Uh, this implies that 2 is 2. This is fine. If you started with the same number, then they are the same, obviously. But then think about our case here. Where can be our I and J here? What's our I and J here? What's the choices of our I and J? Sorry? Huh? Actually, our I and J just run from 1 to 5n. Meaning what? This is like any number that are less than or equal to 5n. When are these two numbers the same? Congruence. These numbers are like filling up the remainder. You get what I mean? You get what I mean? So for example, like maybe I give you a larger example here. Okay, how about mod 9? Okay, and then you consider all the ij between 1 until 9, let's say. Okay, you want I congruence j mod 9. Okay, is it possible that 2 congruence to 4 mod 9 or not? No, right? Okay, so the only possible case is like 2 congruence to 2 mod 9. But then this is saying that 2 is equal to 2. Actually, they are equal as a number. Does it make sense? Okay. If you consider any number less than n, right? If you want them to be congruent with each other, they have to be the same number. Okay, because they represent the different what do we call it? Different classes or different representative in the complete residue system. Right? No? Any integer belong to one of this uh, is congruent to exactly one of these integers. Okay, so because the I and j we consider is less than 5n, okay, is less than 5n. If they are congruent to each other, they have to be the same. Okay. You cannot pick any different two number that's less than 9 but congruent to each other. Okay, they have to be started with the same. Does it make sense? Okay. Okay, so you can remember this examples to tell you this. Okay, so that's why taking different power up to 5n, you will get a complete residual system. Okay, they are different and they are relatively prime. Okay, so this is one part of it. The other part that we finished off last time is this theorem here. So if the order of A is t and u is a positive integer, then we can figure out the order of A to the U. Okay, A to the U is just T over the common divisor. No, not just common divisor, but the greatest common divisor between T and U. Okay, to show this is also not very hard. Okay, it's not very hard. Maybe we can quickly do it. Okay, so well, there are two things to do here. We're gonna use this strategy. So we're gonna use that order of AU will divide T over the GCD between T and U, and order of, sorry, the other way around, T over the GCD of TU will divide order N of AU. Okay, so here we'll say that if A divide B, B divide A, this will imply that A equals to B. And this is what we want. Okay. Well, you can show this using the definition we learned last time. Otherwise, to convince yourself, maybe think about maybe 2 over 2, 2 over 2, then 2 equals to 2. Okay. Maybe if you don't believe, you can try other method, right? If you 2 over 4, is it possible that 4 divide 2? No, right? Okay. So this divisibility it's not just about remainder, but the sum order coming in here. Okay? So usually you divide a larger number, but then if the number is strictly large, you cannot swap the divisibility around. Okay, does it make sense? Okay. I mean, the easier version of this you will see in mathematics usually is if you will show that A is less than or equal to B, B is less than or equal to A, then this will implies that A equals to B. Okay. Yeah. So divisibility here has more structure than ordering. Okay, but then we will use divisibility for this case because for us it's more convenient. Okay, how to show this? How to show the first two here? Okay, so so what to do here? Obviously, we have to use our condition here. Okay, this order we need to know about this order of A is T. Order of A is T means what? A to the T is congruent to 1 mod n. Okay, 1 mod n. Okay, so first thing we'll do is not that, not that. What is AU to the power of T over the GC of T? Okay, well, we can swap this around, right? Become A to the T to the U over T comma U. Okay, but this part here is just integer. Correct or not? You divide by your GCD. Okay. But then what is AT? By assumption, what is this? Order of A is T, right? So this means what? The inner part will evaluate to 1. Okay, 1 to everything is just 1. Okay, so this is 1. Okay, so why do I want this? What does this say? What does this say? So last time we know that the order of AU will divide any power that makes AU to 1. Does it make sense? Order of AU is the least positive integer such that AU to something is 1. So the rest, the other power will get divided by this order. That's how we get one type of divisibility. Make sense? Okay or not? Question? Any question? Any question? Is everyone okay with this solve here? Still remember the property of order. Order will divide any other power that make it to 1. Okay. Maybe I could show you quickly that theorem. Yeah, this one. Okay. So if you have any other order power that makes A to 1, the order of A will divide it. Okay, if and only if. Two sides. Okay. How about the other side? The other divisibility here. Yeah, so we left with this one. Okay, we left with this one. Well, second, not that. Also, AU to the order n of AU is 1 mod n. This one is by definition, right? Okay, by definition of the order. Right, everything to its order is congruent to 1 mod n. So what does this mean here? Maybe I can write this a bit different, right? So I can group my U and the order together. Okay. So for this we can compare what? So we can compare to the order of A. Correct or not? A to something is congruent to 1. So meaning what? The order of A must divide this power here. The order of A is T. Okay, so the order of A, which is equals T, must divide U times the order of A. Okay, T divides U times the order of A. But not quite what we wanted yet, right? Okay, we want T over T, comma, bracket T, comma, U, bracket, divide order of A. But here we got an extra U here. Okay, not quite what we want. Not quite what we wanted. But any idea how we proceed? Okay, well, well, we can differentiate both sides with the GCD, right? Okay, so what's our GCD? GCD of T and U. Is Sora okay with this step here? If you don't like, maybe I can write like this. So U times order of NAU equals to the multiple of T, right? Then I just divide both sides with the GCD of TU. Okay. Okay, because the GCD of T and U can divide T, can divide U. Okay, still integer, everything here. But then what do we see here? What do we see here? So here there's a very important observation, right? You have removed the GCD means what? You remove all the common divisor between T and U. Okay, so meaning what? Meaning T over TU, comma U over TU, their GCD is 1. Okay, so meaning this term here cannot divide U over TU. So it means that T over TU must divide the order of A, which is what we wanted. Okay. Following? Following? Any question so far? No? Okay. So maybe some of you are worrying about proof, right? But proof is not accessible in this class. But then maybe I will try to show some proof here so that you are more familiar with the definition. Okay, but definition and calculation will definitely test the course. Okay, so if you can follow this kind of proof, then it will be an add-on to this course here. Okay. Otherwise, if not, then this statement here is pretty important for you. Okay, how about we try some problem? Yeah, let's try some problem. Okay, example. Okay, show that 7 is a primitive root of 10. Then find the order of this very big number here, 7 to the 26. Okay. So remember that just now our statement is about order of some number to a large. Okay, let's see how we do this. So how to show that 7 is a primitive root of 10? When is a number a primitive root? You need to check about the, before checking about order, we will see that 7 is relatively prime to 10. Okay, good. Next, we want to show that the order of 7 is 5. 10. Okay, so what's 5 10? Huh? 4. Okay, so how do you calculate 5 10? Uh, uh, 5 10 is just 5 2 times 5 5 because it's multiplicative. Okay, we split into prime powers. And then 5 on power prime is p minus 1. Okay, so you get 4. Okay, otherwise you list down what are the four numbers that are relatively prime. 1, 3, 1, 3, 7, 9. Yeah, okay, good. Okay, so then you will check whether the order of 7 is 4 or not. Okay, so how many number do you need to check? The order of 7 must divide 4. Okay, so you just need to check for 7 to the 1, 7 to the 2, and 7 to the 4. Okay. Order of 7 must divide 4. So what are these? So 7 to the 1 is 7 mod 10. 7 to the 2 is 49, which is minus 1 mod 10. And then 7 to the 4 is 1 mod. So order of 7 is 4, and 7 is a primitive root of 10. Okay, so you know the order, and then you want to find the order of the power of 7. So what do you do? What do you do? Hmm, What do you do? So what's important here? Okay, look at this statement here. Okay, if you know the order, then order of A, then you will know the order of A to some power. So you take the order of A, divide by the GCD of your order with the power. And so in this case here, what is it? The of 7 to 26 is just 4 over the GCD of 4 and 26. So you get 4 over 2, which is 2. Yeah. Okay, so far any question here? Any question so far? Mm, sure. Any question so far? Is it okay? Is it following? Yeah. Okay. The back, okay. The front, the side, okay or not? Okay. Okay. Okay, good. Let's continue. So which one should we do first? Let me see. How about do this one first? Find all the incongruent primitive root mod 26. Okay, so how are we gonna find this? I think to find this the way we do quite primitive. Okay, let's do this. Okay, find all the incongruence primitive root mod 26. So how should we start? So what's the keyword for primitive root? First of all, you want the GCD between this root with 26 is 1. And then second, you need to check the order of your uh, element, whether it is 5 or 26 or not. Okay. So these are the two things you need to uh, check. So not that 5 or 26 is what? It is 5, 2 times 5, 13, which is 12, like that. Okay. And then what are the candidates you can take uh, up to 26? Actually, there are a few. Okay, so they are like 1, 3, 5, 7, 9, 11, 15, 17, 19, 21, 23, 25. Okay, quite a lot because you really just remove those with divisor 2 and 13. Okay. But then how many order that you need to check? I mean, how many power that you need to check to confirm the power of A? Also quite a few. Because 5 of 26 is 12. So there's a few divisor going on here. So you need to check like 1, 2, 3, 4, 6 before you go to 12. Okay, before 5, 6. 6 times you check. Okay, so you know what to do next? I let you check. Or should I show you one? Okay, maybe I show one. Okay. So first of all, I mean the easiest one is 1, right? 1 is never a primitive root because 1 is already 1 more 26. You cannot. You already go to 1 earlier than power of 12. Then maybe you can check 3. Okay, how about 3? Okay. Next. 3 1 is 3. Okay, obviously, which is not 1. But then next one to the square is 9, which is not 1. And then 3 to the 3 is 27. Again, not 1. Uh, 1. Oh, 1. Oh. Wait, what am I doing here? But 3 is not 12. Oh, okay, good. So here is 1. But then 3 is not 12. Okay. So 3 is not a primitive root. Okay. Yeah. So I give you maybe a few minutes to check the rest. Yeah. Yeah. Do you want to try check the rest? Let me see. Yeah, I check everything. Okay. Yeah. How many more to check? Quite a few. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, maybe the first row will uh, check 5 to 11, and then here we'll check 15 to 19, and then the other one will check 21 to 25. Okay, yeah, let's spend 3 minutes to compute this. See which one of them is a primitive group. Anyone finish computing? Anyone finish computing? Okay, maybe the number is getting larger and larger. But then we will have another method to do this. Okay, we'll have another method to help you. Okay, so here is the method. So, well, let's go maybe two more, and then I'll tell you what's the method we can use here. So if you go on checking 5, 5 is not primitive root also, okay, because it goes to 1 at power 4, okay, so 5 is not primitive root. But then if you go a bit further, which is 7, what you will see is 7 to the 1 is 7 mod 26, 7 to the 2 is 49, which is negative 3, which is not 1 mod 26. And then you go a bit further. What else we need to check? 7 to the 3 also. Okay. And the 3, you check that it is actually 20, negative 21, which is 5. Okay. And then 7 to the 4 is 9. Negative 3 squared, 9. And then 7 to the 6 is, what's this? 26, right? So it's a negative. Hey, what's the number? Not 26, 25. 25 to, okay, which is negative 1. Then only then 7 to the 12 is 1 or 26. Okay, so we know that 7 is a primitive root of 26. And then you will get a reduced residue system from here. Okay, 7 to the 1, 7 to the 2, up to 7 to the 12. Okay. Uh, yeah. So where's my corollary? I didn't teach you this corollary yet. So here, this corollary will come to a safe. Okay, so if you have a primitive root here, well, what are the other primitive root? You can see that r to the t is a primitive root mod n if and only if the GCD between t and phi n is 1. Okay. Why? Why is this true? Because you remember we can get the reduced residue system from the power of r. Okay, we can get all of them using power of r. And then you want to ask again, which one among these are primitive root? Okay, which one among these are primitive root? And then here it gives you a condition that as long as your power, okay, with the phi n has GTD 1, then r to the t is a primitive root. Hmm. Why is it working here? Okay, so maybe I can show you here. Maybe prove this very quick. Okay. Suppose r is a primitive root of n. Okay, then what's the order of rt here? Okay, what's the order of rt here? So by the previous theorem, right? We know that order of rt is just order of r divided by the GCD between order of R and the power. Okay, this is what we know by previous theorem, and we use this to do computation. Okay, but then what? But then the order of R is just phi n, because it is a primitive root. So this one is by assumption, by this assumption. Okay, but then you want this order of RT to be phi n again. Okay, so for RT, R to T to be a primitive root, you want that order of RT is phi n. But then on the other side, you know that this is phi n over T over phi n. So how is this two number the same? How is this phi n over something equal to phi n? It means that your denominator must be, okay, which says that T and phi n have to be relatively. Does that make sense? Okay. Okay, so for these two to be the same, this implies that the denominator have to be equals to 1. But then this is just saying that T and phi T is phi n is relatively. Make sense? Okay. So from here, you can figure out all the incongruence primitive root by just seeing that if 7 is a primitive root of 26, okay, and how to find the rest of them. So 7 to the T is a primitive root again, 26, if and only if the power and phi n are relatively prime. So how many of them? So hence all incongruent primitive root mod 26 are 7 to the 1, 7 to the 5, 7 to the 7, and 7 to the 11. Okay, and then you can try and check what are these three. Okay, you can check what are these three. Yeah, maybe you can try and check what are these three. Which one? Okay, so far any question or not? No? No? Okay. Yeah. So there's a theorem here. So if a positive integer n has a primitive root, then there is a total of 5 phi n of incongruence primitive root. Okay, phi of phi n. Why got 2 times? Why is there 2 times here? Why do you need to do 2 times? Still remember what does the first phi n do? So I think this proof is very quick. So if you have a R be a primitive root mod n, then you really only have phi n of candidate to choose from. Okay, phi n of them. But then you want them to be primitive root. So just now says what? This forms a reduced residue system. Okay, so you only have phi n candidate to choose for your primitive root, but then which one of them are the primitive root? You want that Ru is a primitive root mod n if and only if the power and phi n are relatively high. Okay, so there are 2 times here. 1 time, 2 times. So 5 phi n. So they are exactly phi of phi n of primitive. Okay, any question? Question here? Or I shouldn't highlight this. Maybe I highlight this one. Okay. Okay. So this phi n is coming from the GCD of R and N, right? So you first reduce your candidate and then found a primitive root and then look at the primitive root with power up to phi n and then search for or you upgrade your GCD to the power. Go to the power and find those relatives. Okay, then these are all the primitive root for model. Okay. So now we introduce you a strategy that once you found one primitive root, you can find all the rest. Does that make sense? Okay, you found one primitive root, take power, and then that power is relatively prime to find that these are all the primitive roots. Okay, from one to all. So that you don't need to check one by one, so many choices. I mean, the number is getting larger and larger. Okay, so this will be more efficient. You just look at the power. Yeah. Any question? Question? So far, okay. Okay. Before we break, maybe I can try and ask. If we're gonna do replacement, what time is good? Maybe no need all of you to come, but at least a majority of you could come. Okay, yeah, at least majority of you could come. So I got a few choices here. So I list down with preference, first preference, second preference, and third preference. Okay. So okay, see how many of you can do Wednesday morning. Wednesday morning. Can I see? Huh? Got class. Oh, got class. No, it's okay. Just want to see like which one is majority. So can I see Wednesday hand? Wednesday hand. Wednesday morning. Last one. They can join this replacement. Yeah, they can join. Okay, one more time. Okay, not too bad. How about Tuesday? Tuesday. Okay, well, Tuesday seems better. Okay, okay, good. Thursday. Okay, I think Thursday then. Tuesday, sorry. Maybe Tuesday. Maybe Tuesday, more people. If you cannot make it, you could just watch recording. Because we cannot find a time that work for everyone here because you guys are taking so different elective. Okay, yeah. So Tuesday is majority, so we'll pick Tuesday. So I will depend on office. I don't know whether they are free or 9 o'clock, 10 o'clock. So I will let you know again. Okay, then so we pick Tuesday. I think it will happen on week 5. Week 5. Okay, yeah. Once I book a room, I'll let you know. Okay, so let's break until 11:06. 喂，哪一个？还没来。对，这个是，这个就是那个primitive root 吗？刚早上讲的对吧？嗯，我看一下这个东西，
嗯，
这个是呀，I mean like 我不，你问什么？你说这个我们有教过，
就是这个公式
这个不是公式吧？那个
定
也不是定理，因为你这里什么都没写，这只是两个 equation 吧。这个只是告诉你说 a 和 m 是 relatively prime，然后这个只是告诉你说 a 的这个 power 是一，就这样吧。嗯
但是我查的时候是这个定理，
它的定理的那个 statement 是
我就是这个条件，在这个条件下，然后这个乘
不会啊，这个不会永远成立吧？我想一下会吗？
这个
我想一下，你说这个永远成立啊？
好像是。
我想一下，会吗？
当时我查这个的时候，他给我提供的这个，
好像是，好像是，这个是从这里来，这个是从这里来，这里，对吧？对啊，因为这一个会永远 divide 它，所以这个是这个的倍数，but then a to 的这一个已经变成一了，明白吗？
好像
呀，你记得这个吗？就是说，如果它 relative prime，order of a 一定会 divide 这个 phi n。order of a divide phi n 的意思就是它可以写成它的倍数，对吧？写成它的倍数，对不对？然后现在你考虑的是 a to 这个东西，对不对？然后你 a to 的这个东西就是 a to 的 order of a 乘这个 to the power k，但是这一端就是一来，就是一。
那
嗯，
这个定理是这个，是原来的定理是这个是吧？
没有，这个不是定理啊，这里只是一个条件嘛。
原根的定义是什么来着？当时没有跟上。
哪个？
就是原根的定义。
原根哈，primitive root 哈。当这一个等于这一个的时候，t 就是 n 的 primitive。
原根的定义是什么？
对啊，就是呃，我想一下，原根的定义就是原根呢，原根的定义就是这两个条件，你这个根要跟 n 是 relatively prime，还有它的 order 是 prime，你要检查这样。你还记得这个例子吗？
记得。
呀，
嗯，
嗯
这个例子，这个例子，等一下，
嗯
看一眼。
嗯
就是这个例子，就是我记得之前有一个例子，就是说，好像是在那个就是七的平方，好像是七的平方，
你的平方呢？
这样还那个
嗯
就是
嗯
假如说，
嗯哼
假如说这里的三的三次方，然后摸的七，然后也是个一的话，那它三就不是原根，是吗？
对，如果他提早去到一的话，就不是，他一定要在他第一次去到一一定要是反的， 哦，那个例子就刚刚做的罢了，就是我们刚刚做的，就是这个，如果他提早去到一，他就不是 primitive，他一定要在 find n 的时候去一。
没太跟上这个环节，就是说这个不能证出来的是吗？
这是不能证明的，这不能，这个能啊，我们就在证这个早上，这是证出来的，对，这是一个天然来的，对，哎，刚刚我们证这个，这个
这个 WTS 是什么？
one to show，one to show，想要这个，
反正你是作业的时候可以用这个吗？
可以用这个吗？不可以。我只可以用我班上那个，除非你用我班上那个推出这个，就是刚才我解释的那个，
可以用上面这样。
这肯定可以，因为这是我介绍的啊，这一个我没有直接说，除非你可以从我说的东西推出来。
谢谢。
Whether can I prove like this question 4?
Oh, Chinese related term.
Yeah, like this.
I think you can. I think you can. I think you can use it.
Uh, First, just to divide two situations. But for this situation, it's not easy to
This one,
express. But
this one is not easy.
it's not easy to express. But
Oh, let me think. Me, 7 divide n. What do you mean? You mean p divide this implies that p divide this?
actually, there's no meaning for this one.
What's this error?
There's no meaning for this error. Because
Then you shouldn't put the
Okay.
error. Yeah.
Okay.
Okay. So p divide. Yeah. So
But for some number, that 7 can divide n, but 11 cannot divide n.
Sure.
Yeah, but it still satisfies that situation.
Oh, okay, okay.
Yeah, and then so if for this 11 like 11 not divides, and then we just come back to this use Woodard's rule or Feynman's leader rule.
Okay. 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 Okay.
Yeah, that's right.
Yeah, I think so. Yeah.
Yeah. Okay. Thanks.
Okay. Let's continue. So, next part of the course, for this chapter, we'll be dealing with which integer have primitive root. Okay. We didn't show you any number that doesn't have a primitive root, right? But it's not on my head either. So let's not give you some example. Maybe I can show you next time. Okay. So for the next part of this course, I think I should tell you a definition first before telling you this theorem. So let fx be a polynomial with integer coefficient. So we say that an integer c is a root of fx mod m if you substitute c into your fc and then calculate the number, you get 0 mod m. Okay, so maybe I give you some examples. So let's say x plus 2 mod 3. Okay, so this is my fx. Okay, this is my fx here. Then we can ask is 2 a root of fx? Okay, so you evaluate. So what is f2? F2 is 2 plus 2, which is mod 4 mod 3, which is 1 mod 3. Okay, so 2 is not a root of fx. Okay, can you find a root? What is the root? Huh? 1. Okay, so you can check. On the other hand, f1 is 1 plus 2, which is 0. Okay, which is 3 or 0 mod 3. Okay, which is 3, but 3 is 0 mod 3. Okay, so 1 is a root of fx. Does it make sense? Okay, so this is a bit different from your calculus. In your calculus, what's the root of x plus 2? Is minus 2. Okay, but here our x is just considered up to 0, 1, 2. Okay, so you just check f0. What's f0? F0 is 2. It's not root. F1 is equal to 0 mod 3. It's a root. F2 is 1 mod 3. So does it make sense? Okay, so the number system here is a bit different from real number. So please be careful. Okay, so if c is the root of fx, right? So any integer congruent to c mod congruent to 2 mod 3 here is also a root. For example, if you put 3 plus 1, 4, if you put 4 into it, okay, it's also a root. Okay. Does it make sense? Okay, so the root here are taken from integer. So f in particular, f4 is also 0, f7 is also 0, and so on. Okay, so these are the root of x. So far, okay or not? Okay. Maybe give a few more examples. Second examples. So how many root does fx equals to x squared plus x plus 1 has? I haven't tell you what mod, right? So mod 7. Okay, how many roots? Huh? Actually, there are 2 categories, right? Okay. So one is, what are they? Sorry? 2 and what? 1 is 2, okay, because 2 squared plus 2, 4 plus 2 plus 1 is 7. There's another one. Huh? 4. Okay, so the other one is 4. Okay, and you consider all up to mod 7. Okay or not? Okay. Okay. So this phenomenon actually it resemble what you see in real numbers. Okay, in real number case, the number of root should be equal to the number of your highest power of your polynomial. Okay, so for example, if you degree 3, so in this case, it's degree 2, okay, because the highest power is 2, we'll say that this polynomial is degree 2. So if you have degree n polynomial, then you will have n root. Okay, in complex number. Okay, in numbers theory here also similar. Okay, for example, how about this polynomial here? Oh, I don't have mod. Never mind. Don't discuss this. I don't know where I get this example. Maybe I can complete it next time. Okay. Basically, I found a polynomial that doesn't have a root. I forgot what is mod over what. Or maybe you want to guess. Can you make it such that there's no root? No root. Can you make it such that there's no root here? I'm trying to give an example that has no roots, but turns out that I forget, like I miss out what's the mod here. Like modulo 1n. You want to try? I guess 3 has root, right? Because if you put 1, there is 1 plus 3. About 4. I think 4 works. 4 works. There's no roots here. So if you put G0, you get 2. G1, you get 3. G2, you get 6, which is 2. And then G4, you get, not G4, G3, sorry. G3, you get 11, which is 3. So no root. Okay, no root. Okay, has no. Okay. Okay, good. So this is about root. So what's the theorem here? So if you have a degree n polynomial here, so the highest power of x is n with integer coefficient, meaning all these ai here are z. And the leading term, meaning the highest coefficient, okay, the coefficient for the highest power term is not divisible by p. So p doesn't divide an. Then fx congruent to 0, mod p has at most and incongruence root mod p. Okay, at most, not exactly n. So slightly different from our fundamental theorem of algebra. Okay, fundamental theorem of algebra say that if you have degree n, you must have n. Okay, at most n of them. Okay, you cannot get more than it. Okay. So far, so good. Yeah. Okay. Next theorem. So if P is a prime, okay, so we restrict our attention to this particular polynomial here, x to the d minus 1. So what's this d here? So d has to be a positive divisor of p minus 1. So p is if p is a prime, p minus 1 would be even actually. I mean, for large prime, it's just odd. I think only, yeah, because if it's even, then it's not prime. Okay. The only even number that's prime is number 2. So you must have a positive divisor for p minus 1. One of them is 2, okay, because it's even. Then x to the d minus 1 has exactly d incongruence root mod p. Okay. So this polynomial is special. Just now Lagrange theorem tells you that there's at most n of them. But then if you look at this specific polynomial here, it has exactly d. Okay, you can find d different incongruence root here. Okay. Yeah. Okay. Next. I think I won't prove it to you for the previous one, I guess. Let me see. Prove it again. Okay, maybe not important. Okay. Next lemma is again the same condition you had. P is prime and then D is a positive divisor. Then the number of positive integer less than P of order D does not exceed 5P. Okay, so what does this mean? See, what does this the number of positive integer less than p of order d mod p does not exist 5. Is useful or not? This statement is it useful? Okay, so do you know what this means here? So if you look at all the number of positive integer, right, less than p, that have order d mod p, it doesn't exist by d. Okay, there are a few things to do here. So first of all, okay, let's take some examples. Okay, so how about look at 7? Look at 3 enough. 7, okay, 7. And then the positive divisor of p minus 1. Well, there are few choices, right? You can take 2, 3, or 6. Yep. Okay, or 1 actually. So you want to ask the number of positive integer less than p that has order d. Okay, so meaning order a power d, okay, which is congruent to 1 mod. Okay, and then the number of them, so how many candidate of them shouldn't exit 5d. Okay, should I make a table for you to see what's going on here? Okay, so let's do it. So what is 5d here? Okay, 5d, what's d here? Yeah, d, there are 1, 2, 3, 6 of them. Oh, 4 of them. 1, 2, 3, 6. 5d here is 1, 1, 2, and 2 minus 1 times 3 minus 1 is 2 again. Okay, good. Okay, so you want to ask that whether how many positive integer that has order 1, order 2, order 3, and order 6. Okay, order 1, order 2, and order 3, and order 6. Okay, so A such that order of A mod P is D. Okay, like that. Okay, so obviously 1 has order 1. What else? How else? What are the rest? So what's the order of 2? Okay, 2 to the 1 is 2, to the 2 is 4. Okay. And then 2 to the 3 is 8. Okay, which is 1 mod 7. Okay, so meaning 2 has order 3. 3 then? Number 3. How about number 3? 3 to the 1. I think we calculated this before, right? 3 is a primitive root mod 7, right? Yeah, so 3 is somewhere here. Okay. How about 4? 4 we haven't calculated before. 4, 1, 4, 4, 2, 16, which is 2 mod 7. And then 2 to the cube is 8. Okay, so done. So here we got a 4 here. And how about 5? 5. 5 to the 1 is 5. 5 to the 2 is 25. So which is 4 mod 7. But then, I don't know, 24. Okay, good. So 5 to 3 is 20. 20 is minus 1 mod 27, right? Okay, so 5 is a primitive root. 1, 2, 3, 4, 5, 6. How about 6? So 6 to the 1 is 6, 6 to the 2 is 36, which is 1 mod 7. Okay. So can you see this? Okay. So the number of positive integer less than p of order d does not exist ID. Okay. With order d does not exist ID. Okay. So 1, 1, 1, 1, 2 of them, 2 of them. You cannot have more than 5D numbers that have order. Does it make sense? Okay. Yeah. I think the proof is also very interesting. I'll see if I want to prove it next time. Okay, then the corollary is actually every prime has a primitive root. Okay, every prime has a primitive. Okay, every prime has a primitive root. Actually, we know how many of them. Do you know how many of them? Actually, we know how many of them. Oh, this one does not exist. Actually, we can prove that actually it's equal. Okay, it's equal. So the number of positive integer less than p at order p is actually equal to 5D. Okay, so just now the lemma tail does not exist, right? Actually, you can show that it is equal. Okay. Yeah. Okay, so in this case here, every prime will have a primitive. Okay. Every prime has a primitive. So how many of them are? Actually, there are 5 of p minus 1 of them. Okay, 5 of p minus 1. P has 5 of p minus 1. Okay, because you are looking for d equals to p minus 1. Okay, the order of primitive root is equals to 5. Because p minus 1 is 5p. Okay, so this matches up with what we know just now, no? 5p. Okay, 5p. Yeah, that we know. But then that statement didn't talk about existence, but this theorem talk about existence. It has exactly 5p of them, which is p minus 1. Okay, so far okay or not? Okay, so let's do one exercise. Okay, find a primitive root of all odd primes that less than 25. Okay, so let's do one examples. Okay. So first thing to see that is in this calculation, I want you to see that actually 2 is a primitive root for a lot of primes. Okay. After you do this exercise, right, try and see that actually 2 can be a primitive root for many primes. Okay. A lot of prime 2 is a primitive root. So meaning you need to take the power up to 5 so that 2 to the 5p is 1. Okay, so how many things you need to check here? Well, you need to check for all the odd primes, right? They are less than 25. So which are these? What are these? Okay, so these are 3, 5, 7, 11, 13, 17, 19, and 33. You need to check for all this. Well, first, you can jump straight to 2. First, start with 2. 2 is the smallest number you can try. So first, you can see that 2 is a primitive root of 3. Okay, because to the 1 is 2, and then to the 2 only you get 2. Okay. Then again, you do the same thing, basically. Okay, you do the same thing, check. Maybe 2 is again a primitive root of 5. Okay, check 2 is enough. Okay, what's the calculation here? 2, you start with 2 again, start with 4. And then from here, I guess you can roughly quickly see that you can get to the 4, get to the 1 by to the 4, to the 3. Just for safety, you can see that it is 2, which is not 1 or 5. Okay. Okay, so 2 is again a primitive root 5. So for the rest, you can check easily. Here's the table. Okay, you can verify that these are the primitive root mod. And then from here, you can get all the other primitive root. Okay, so why are we doing this? Let me see. Is this any useful? Is this just trying to prove to you every prime has a primitive root here? Let me see. Okay, maybe not very interesting on this example. Kind of boring. Never mind. Okay, next go to the next one. For every odd prime number p that is less than 25, find the order of 2. Okay, so for this case here, it's the same example, really. Okay, so you can see that few of them we already know already. Okay, so we already know for the case of like 3, 5, 11, 13, 19. Okay, these order of 2 should be p minus 1. Okay, because they are the primitive group. But for the rest, what do you expect? What do you expect the order of 2? For the rest, what do you expect? How do you compare to p minus 1 or 5p? What's the order of 2 for the rest of the case? How do you compare? How do you compare to 5p? Less than or equal or greater? Should be? Should be what? It's not a primitive root, or what does it mean? Sorry. Okay, not trying to get what I say, huh? Okay. So if you are not a primitive root, what could happen? What could happen? You go to 1 earlier. Okay, so meaning the order of 2 should be strictly less than 5p. Okay. But then last time we also know that the order of 2 have to divide 5p, right? Okay, so it's one of the divisor. Okay, yeah, I think this concept is not very used to you because just now someone come back and ask me here again because you are not very clear about this thing here. This statement here, I guess you need to kind of memorize here. Yeah. Where is it? Okay. Yeah, this one. Okay, this is very important. And the order of A have to divide any power that makes A go to 1. Right, this is very important. So this also says that order of A has to be less than or equal to X. Okay, so order of X, remember, is the least power that makes you equal to 1. Okay, this is very important. We are just trying to play around with this every time. Okay. Yeah. Okay, so you only need to find for these three cases here. Okay, you just need to find for these three cases. That's it. Yeah, these three cases. But for the rest, it's just p minus 1 because they are the primitive root. And then you see in the previous example. I think for the rest, yeah, yeah. Unless you check it, otherwise you do it again. Okay. So I'll leave it for you to find this. Okay. Next, shall we do this or do an example? Let me see. Okay, maybe we do theorem first. Okay, next theorem. So if P is an odd prime, okay, and R is a primitive root mod P, then the order of R mod P square. Okay, so we upgrade our modulo here. We instead of P, we go to P square. Is P minus 1, or the order of P square of R is P square minus P. P square minus P. So what's about P square over P here? Do you still remember this number? Or maybe what is 5p square? Anyone still remember what's the formula for this? 5p square. Huh? P square minus p. Okay, so what does this theorem say is if you have a primitive root mod p, can this primitive root be the primitive root for mod p square? Okay. It can be. Okay. So there are two cases, right? Either p minus 1, either it is a primitive root for p square. Okay. If the second case happens, then it is a primitive root of p squared. Okay. So this maybe I write down here. The later case here implies that R is a primitive root for p squared. So either the order is p minus 1 or p squared, or it is a primitive root of. Okay, let's prove this. This is a very nice exercise here. Let's do this. Okay, since R is a primitive root mod P. Okay, so what does primitive root mod P means? So the order of R should be 5P, okay, which is P minus 1. Okay, good. Second, again, note that R to the order of P square R is congruent to 1 mod P squared, okay? If you have 1 congruence mod P squared, right, what does this mean? This means that you are actually 1 plus a multiple of P squared, right? So, but then you can interpret this as Kp times P, right? So this is saying that this is also 1 mod P. Okay, 1 mod P. So what does this mean? So this means that P minus 1 or the 5P have to divide order of P squared. Okay, because this 5P is the order of R. Okay, make sense? Okay. Order of R mod P must divide any power that may be. Right? This is very important point you have to remember. But on the other hand, what do we know? On the other hand, we know that order of R mod P square, okay, should also divide 5P squared. okay, which is p square minus p that you told me just now. Okay, so this form a very nice squeeze condition here. You have p minus 1 dividing the order of p square r, and you have this number dividing p times p minus 1. What could happen here? What could this number be? What could this number be? You must be at least containing p minus 1. But then you cannot contain too much things, right? Yeah, because you have to divide p and p minus 1. So, what are the possibilities here? So, hence, the order of r should be p minus 1 or really just p times p minus 1. That's it. Okay, two possibilities. Okay, you cannot contain too many. Does it make sense? Okay, you must at least contain p minus 1. And then what else you can contain? You can contain 1, then you divide p times p minus 1. Then the next thing you will try to consider is p times p. Because p is prime, right? There's no much room you can play here. Okay? Unless this p has contained other common devices, other devices, so you can slowly put the devices. Otherwise, it's just either you want to add a 1 here or either you want to put here because p only has 2 devices. Okay? Does it make sense? Yeah. So note that p is prime. So we only have this condition. So the divisor is just 1 and p. So two conditions, two possibilities. Okay. Let's use this to do exercise. Okay. A bit boring, huh? This exercise. So many proof. What do you mean? Proof or exercise? Proof is boring. Calculation not boring, you mean? Okay. So let's calculate now. Okay. I mean, to me, calculation is boring. Okay, it's okay. Never mind. Different taste. Okay, let's do this then. Find a primitive root of 25. Okay, so maybe we can start with some hints, okay? Because we already know that by previous example, 2 is a primitive root of 5. Okay, we know this already. So shall we find it for 25? Okay, let's do it for 25. So we have this theorem tell us that, where's our theorem? The order of R, okay, so we have a primitive root, to p square is either p minus 1 or p square minus p. Shall we do this? Okay. Let me see. Okay. Right. How about we bring this statement here so that we no need to flip it again and again. Would be short lip. Easier. Okay. So so if the order of p square, so order of 25, order of 2 mod 25 is p square mod p, then we found a primitive root of 25. Okay, let's try. So So there are two things you need to check only, right? If it doesn't go to 1 by p minus 1, then it should be a primitive root. Okay, so there's only one thing you need to check here. Okay. So by this theorem, if the order of 25 mod 25 of 2 is not p minus 1, then 2 is a primitive root of 25. Okay, good. So let's check this. So 25 minus 1 is what? Is sorry, not 25 minus 1, huh? This is p, huh? So 5 minus 1, which is 4. Okay. So you just need to check 2 to the 4, is it 1 in mod 25? So in this case here, what we are trying to do is we know a primitive root of, not just now we proved that every point has a primitive. And then we want to know about primitive root of p squared. Okay, over here is 5 squared. Okay, so basically we don't see this as 25. We chop it out using prime. So it's a 5 squared. Okay. So let's check. Very easy check, right? So checking. So 2 to the 1, 2 to the 2, 2 to the 2 to the 3. Okay, 2 to the 4. No need 3 to help you calculate. Just do this. So you can check that 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 4 is 16. Definitely is not 1 mod 25. I think you are good. Okay, I think you are good. Okay, so so in this case here, so so the order of 25, sorry, order of 2 mod 25 is not 4, implies that order of 2 mod 24 is p squared minus p, which is 5 of 25. Implies that 2 is a primitive root of 25. Okay or not? Does it make sense? Okay. So the lesson for this theorem is if we know about the primitive root of p, then we can know about whether this is a primitive root for p squared or not. Let's go one step further. Okay, for p squared, do we know about it? Okay. At the same time, you actually can check that 3 is also a primitive root of 5. Okay, so maybe exercise. Try and show that 3 is a primitive root of 25. Or maybe let me ask you a question. From this 2, right? How do you get that 3 is also a primitive root for 5? Last hour I teach you, right? Or what do you do? From 2 is a primitive root of 5. How to get 3 is a primitive root of 5? So you remember the 5p thing? 5p. Okay, so 2 is a primitive root of 5. So 2 to the power up to 5, up to 5 should be a complete, should be a reduced residue system. Okay, and then out of these reduced residue system, how many of them are primitive root? The GCD of the power with 5 n should be 1. Okay, so how many power are relatively prime to 5n? So 5 here is 4, right? So how many number relatively prime to 4? 1 and 3. So 2 to the 3 is a primitive root. So what is 2 to the 3? 2 to the 3 is 8. 8 mod 5 is 3. Okay. And so 3 is a primitive root of 5. And then you go and check for 3 to the 1, 3 to the 2, 3 to the 4 is 1 mod 25. If it's not, then it has to be a primitive. Okay. Question? Got question? Any question? Question? Should I write down or write down? Okay. So the strategy is like this. Okay, so the strategy is like this. So we found A is a A is not a good variable. So let's put R is a primitive root mod P. Okay. Second, R to the 1, R to the 2, R to the 3, blah 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 up to R to the 5P should form a reduce residue system. So why do we care about this reduced residue system? Because not because okay, so R to the I, okay, will be relatively prime to P. Okay, and then from here, Ri will be a primitive root mod P if and only if I and 5P are relatively prime. Okay, so this is the step. Okay, and then now we go to the next step. We want to ask whether when R is a primitive root of P squared. Okay, so this is the next step we did just now. Okay, for P squared. Does it make sense? Okay, so can we go from a primitive root of mod P to primitive root mod P squared? Okay, make sense? Okay, turns out that there's only two things you need to check. Okay, so this power is relatively straightforward. Either is P minus 1, either is P squared minus P. So if it is not P minus 1, it must be P squared minus P. Okay. Okay, so if it is P minus 1, then it is not a primitive root. Okay, because you go to 1 earlier than 5P. 5P squared, sorry. Okay. Good. Good. Bit dry, this knowledge. I think okay, maybe break soon, right? Maybe tell you a bit story. Okay. I have a lot of story because I stay with students a lot. I try to monitor them. I observe how they start. Some student is like I don't like to write, right? I don't like writing. They don't like writing. Do you like writing? You also don't like, right? Okay, never mind. I'm not speaking about you, my student. Don't like to write. But then FYP is coming up. You have to write. You have to write thesis. Okay, you have to write. He said, I don't know how to write. Okay. Then I try to what do you call it? Huh? No, I don't force him. He is not my FIB student. He's like, I mean, I teach you, right? You are different branches, right? I mean, like you are different degree, AIT, CST, whatever T, right? But then I mean, we turns out I have a chance to look at the thesis, so I try to proofread it. Okay, then I give some comment how to change it, whatever. But then he doesn't have enough time to change, so he just submit. So what I want to say is, you don't have enough time, but then when you have enough time, do you spend time like try to sharpen your skill or not? Okay. If you don't do that, there's not enough time. There's no chance for you to do correction actually. Okay. So when you have enough time like this, right? So what do? Do you like just feel boring or what? I don't know. Or you try and think about what am I talking about? Or you try to think what am I trying to say? Yeah. So this is what's your attitude toward things that people say to you is very important. Okay. Are you trying to understand everything what people say, or you just think that, oh yeah, this is boring, then I decided not to listen? Because this is a very important decision. Okay, once you decide this is boring, this is what, then whatever comes next to you, you won't get it. But if you think that, oh, although this is boring, I think I need to know this, then when things come, you don't have enough time, then you can face it. You understand or not? So this is about investment actually. Okay, how you invest your time, how you invest your energy. Okay, then this will pretty much decide your path. Okay, I respect you. Okay, if you want to decide do different things, I respect you. But then you have choice. This is what I want to tell you. Okay, you have choice. Yeah. So this thing is like very boring, it's very technical. This is very true. Very true. Yeah, but then there are ways that these things will get useful. So that's why I told you you have to convince yourself what's your motivation here, or what's your motivation doing anything. Okay, is it just because of your parents forcing you or what? Then that would be very bad. Okay, because I see that the students, some of the students like drop off. The worst case is drop off. Okay, the students go to Korea during weekend to see their idol, but cannot submit my assignment. I mean, you can submit my assignment on Friday and then you go to Korea on weekend. I don't care, right? But then she promised like, oh, I submit to you next week. But next week she didn't submit. Instead, she go to Korea for 2 weeks, consecutively. Why go to Korea? Can face to face or one to one speaking with the idol. Then the idol said, "I remember you." Then she very happy. Okay lah, okay, sure. But then, so think about why you come here lah. Okay, and you understand what I want to say? Yeah. Okay. Yeah. Something is very dry, but then you need to think about what you want to do. Mm. Okay. Yeah, very important, huh? Okay. Okay, how about let's break first? Break until 12:05.哎，
这个我没听懂，为什么这个地方可以给它做是
我看一下，错还是错吧？
错吧？
错应该是错，不然的话没有这么多号。Yeah, yeah.
那我怕是因为它
对，
我说的，我说怎么会有
Yeah, it's okay.
啊？我才没有，我才问他是否理解错问题了。
哦，是吗？哦，我还没改到呢。OK，好。
就是
OK。
好像我把那个这是对，这是我把它理解成每个是单独求的。
单独去哦，呀，因为这个是那个 Chinese remainder，
对，但是
因为它这个
我理解成整个
，I
就一个
see，
reverse。
OK，因为这里是写 system，所以就是一起哦。
我的天。
OK，
没事。
没事。
然后这个是我拿用粗的，
Yeah，
但是这个地方我用那个方法类的是有点疑问的，就是我如果不用的话，好像写不了。但是它好像就是我前面设的那个前提条件，跟就是定义里面的不太一样。
哎呀，好。
但是好像确实是这么写。
不一样的话就不可以。
就是但是这样。
第一次停住没等到我睡觉你懂一次要体验时间。OK，理解出来，理解出来，理解出来，我睡着，把理解给你睡出来，我这样子经常去做这个话，所以我觉得啊，我这个包括
所谓的几来着？
什么是解？
我是
我也忘了。
我
这样，这个，
对，因为它这个就是 undivisible，但是我觉得，因为它这个 n 是没有给出来的，怎么能够就是说明它这个 n 一定是 undivisible？
对，它可能有几种情况呢？如果你不要 divisible 的情况，你可以用这个，只能用这个，或者你要假设两种情况哦，就是
一个是 divisible，
对，
一个是
你个是要另外解了，不 divisible 要这样解了。
如果我用这
个的话就没有关系，它 divisible
就是
对
对
对
对
对，
最近
嗯
那就是
可能要另外解哦，另外一种，
所以说要把那个 divisible 的情况再列出来。
没有错，不 divisible 就这样解了，divisible 就要想另外一个。
另外一个情况，等我再把单独的列出来，可以。单独列，太奇怪了。
请问，
我这个还是它分不同的 M1、M2、M3，但是这个 for M1的的时候，我要考虑 undivisible，然后再考虑 divisible，然后得出来一个总的结论是它和它可以有这样的。我们这个最后要有那个Chinese remainder，把它合并起来。
这个是对的。
但是所以就是这个 format 的一个 series，它这个用符合那个前提条件，我觉得是有问题的。
对，所以这整个的前提条件是，当你的 P 不能抵外你的整个东西的时候，
是整个吗？
是整个吗？不是整个，只要 n 就好了，是吗？
对，
你只
就可以
可以 n 就好，所以全部都在关系到 n 吧的是吗？
对，但是你可以分到就是小的。
这样你要分一个情况，就是 P，当你的这些不可以 divide A 的时候，还有一些情况是，其中一个可以 divide A 的时候，可能可以一起讨论吧，divide N，那些应该可以一起讨论，我觉得。
只是到最后，然后所有的继承11乘以13，然后所有最后可以 divide N，就相当于这个数可以 divide。
你要从头开始，这一个只有这一个情况吧，因为这一个情况是当 P
不可以
divide，那你还有其他情况是 P 可以 divide N，所以意思说可能11 divide P 或者13 divide P 或者。
所以说还是要在
空头
这一个情况里面再考虑情况可以 divide。
不是，他的情况是分这个，他情况不是分这个号码，他情况是分他的 case one 应该是那些P 是 P，但是 case one 应该是这个 MI 不 divide P，你才会出这么多东西嘛。对，不是 P，是 N。你 MI 不 divide N 过后，你才能够出这么多东西嘛？因为你分班里的 t 人都用在这个地方嘛，或者说这个地方，其实这地方这个地方。然后你现在是假设不能够这样用分班里的 t 人的话，就是可能某个 MI 会 divide N，就是说可能7会 divide N 或者11 divide N。
那就是 case two 里面再分3个。
我不知道要不要分三个，或者你可以写一种 argument 把三个都包，但是肯定是
要
你
讨论
这三个东西。呀，可能有一个 argument 是可以直接把三个 case 都讨论的，啊，你可以试一下。Hello, hello, hello, testing. Okay, so let's take attendance first. 贺书月，施杰生，范家豪，OK。李承铉，yes。钟宏庭，哦，OK。朱祥泽，yeah。任波，OK。对，傻了，不，杰森，对，有杰森，OK，杰森，OK。
然后右边我看到
你下面没有看到你，对，好。陈意涵，韩西莹，韩西莹，刘贞贤，张东俊，叶伟通，陈子涵，王金珍，龚一健，陈子，胡崇瑞，陈思曼，嘉诚，冰珍，浩云，浩然，I think I see 浩然 right. Yeah. 彭欣怡，天文琪，张小柔，张泽瑞，陈凯莹，yeah. Tiffany, yes. Check it. Yasin, Jasmine, I think I saw both of them. Jajin, stuff. 梁家月，德兴，韦明涛，杨旭成，曾逸飞，陈玉清，李林毅，陶化元，sorry，曹化元，王雅，李浩聪，刘毅书，潘子良，也，甘金浩，何明轩，李伟航，沙地阿玉，Joy Lee，何明浩，黄子琪，黄黄棋子啊，sorry，棋子吗？Yes，OK。秦子祥，熊培成，张馨予，金鱼，张馨予，OK。周瑞敏，赖文义，陈志，陈子睿，李小环，曾天健，Aaron，瑞全，Isaac，宾科，高硕，王思涵，哦，sorry，思怡，也，明显，双峰，金宁，嘉凯，朵娜，家谱，冲铺，汪冲铺，冲铺，汪冲铺，汪冲铺，武艺，OK。崔文倩，汤旭，冲浪控，嘉怡，泽宇，收思，收思，陈少航，陈卓，李乐山，彭一成，赵新成，sorry。Nor OK。玉涵，玉兴，陈玉兴，恒玉兴，OK。 studying. Yes. Okay, let's continue with this PP square business. The PP square business here. Okay, what's this? Let me see. Which one should we do first? 26. Okay, I give you 3 minutes to do this. Okay, so find all the primitive root mod 11 and determine each of these is a primitive root of mod 1 to 1. Okay, so 1 to 1 is what's the relation between 11 and 1 to 1? 1 to 1 is a square of 11. Okay, so you will use the method we learned just now. Check whether p minus 1 is the order of these primitive root. Okay, so I use this strategy here to do this question. Okay, maybe I show this strategy. Okay, so first found primitive root mod 11 first, and then found the rest by using the power of R. Which power you need to take care of? Just look for the power that's relatively prime to 511. 511 is 10. 510 is 4. We calculate this a lot of time already. So 4 of them will be a primitive root of 40. And then for 4 of these, you need to decide whether they are primitive root mod. Well, yeah, try and compute it. I give you 4 minutes. Okay. Let's check answer. This one. Okay. So first of all, I guess like what we see previously, 2 is a primitive root mod 11, but you can quickly check it. And for the rest, it's just 2 to the k, where k and 5, 11 is relatively prime. So there are 1, 3, 7, and 9. Okay, so if you compute, these are 2, 8, 7, and 6. Okay, 4 of them, because 5, 11 is 10. Sorry, 5, 11, wait. 5, 11 is 10, correct. And then 5, 10 is 4. So there are 4 of them. 5, 5, and so by previous theorem, if their order mod 11 square is not 10, then they are primitive root. So you can check that 2, 6, 7 to the power 10 are not 1 mod 212, but then 8 to the 10 also not 2, 1, 212. So these are all primitive root for mod 1 to 1. So they are again primitive root. Okay, follow this. Okay, so far so good. Okay, so for these are not mod 1 after taking power 10. So they are primitive root of 2, 1. Good? Everyone okay? Okay. Yeah. Okay, so then let's say if it is not primitive root, right? So what can we do? Do we just stop? Actually, no. Actually, you just take r plus p, then it will be a primitive root already. Okay. So if r is not a primitive root mod p square, then r plus p would be a primitive root mod p. Okay, like a magic. I think I won't prove it now. Okay. I'll see if I want to prove it next time. Okay, so does it make sense? Okay, so this theorem says that if r is a primitive root mod p and order of r is not p minus 1, then r is a primitive root p squared, like what we did before. But if the order of r mod p squared is p minus 1, then it's not a primitive root, right? So what do you do? You don't just stop. You just add a p into it, it will be a primitive root. Okay, r plus p would be a primitive root. Okay. Let's see. Do you have example for this? Okay. See, do we have example for this? Okay, so let's do this example for this one. Okay, page 30. These pages are some of them are a bit mixed up, or I rearranged them. So I will post up my version. Okay, so one can show that 487 is a primitive prime number, and 10 is a primitive root mod 487. Moreover, we know that 10 to the 400 is 1 mod 487 square. Find a primitive root mod 487 square. Okay, so actually for all these statements, you should know how to check them. Okay, so first, for example, first statement, 487 is a prime number. Do you know how to check it? You take square root of nearest perfect square and then try and divide it, and then you found that it's not divisible, okay, by all these prime less than square root of the perfect number. And then primitive root, how to check? How to check primitive root? It's a bit a bit daunting. So you need to check that you have to find what's 5 of 487, right? But then this is a prime, so it's 486. Okay, and then you need to check that all the power that divide 486, it doesn't go to 1. So that the order is 486. But then this next statement tells you that 10 to the 486 is already 1 mod 487 squared. Okay, so what does this say? What does it say? This says that the order, okay. So since 10 to the 486 congruent to 1 mod 4x72, this says what? The order of 10 487 square is what? Is strictly, or no, not strictly, is less than or equals to 486. Okay, because the order will divide 486. Okay, but then it has to be uh 486, right? By previous theorem, because there are only 2 possibilities. Okay, p minus 1 or p squared minus p. Then this number here, 10 to the 486, is not a primitive root. But then how to get a primitive root by previous theorem? We just need to add a p to it. Okay, but then 10 plus 487 would be a primitive root. Maybe a bit hard to do checking, but if you like, you can check it. Otherwise, if I got chance, maybe I can prove to you next time. Okay, so the story here is if p is not a primitive root, sorry, if a is not a primitive root for p squared, but then a plus p will be a primitive. Okay. Yeah, do you want to verify this? Maybe you can check this yourself. Kind of hard. Very big number. Okay, any questions so far? No? Okay. Okay. So don't be disappointed if it is not a primitive root, but r plus p will be a primitive root for p squared. Okay. So we just go one level out from p to p squared, how to figure out a primitive root for p squared. That's it for now. Okay, later we'll do for a more general one. Actually, we will do it now. So if p is an odd prime, then p to the k will have a primitive root for all positive k. Okay, so if r is a primitive root mod p squared, then it is also a primitive root mod pk for all integer k. Okay, so this is very strong. Okay, so if you found a primitive root mod p squared, then this exactly the same guy would be a primitive root for all the different pk. Okay, no need to do the trick we do just now already. No need plus PR or whatever. Okay, it will serve the same role in different people. Does it make sense? Okay, so from here, can you infer anything or not? Every prime have a primitive root. Okay, then this primitive root has either order p minus 1 or p squared minus p. Okay, if it is p squared minus p, it is a primitive root for p squared. Then it will serve for a primitive root for other pk. Let's say the order of r is p minus 1 in p squared. What do? You just add a p into your r. It will be a primitive root for p squared. Then this r plus p again will be a primitive root for all the other p. So meaning what? All the prime power would have a primitive root. So this is the corollary. Make sense? Okay, so maybe I draw a chart here. So every E has a primitive root. Let's say R. Then there are two cases. Order of R P square will be P minus 1. And order of R P square will be P square minus P. Then this implies that R is a primitive root of mod P square. And then the above one, what happens here? This will imply that actually R plus P is a primitive root mod P square. Okay, R is not a primitive root, but R plus P is a primitive root. So then by this theorem, R or R plus P is also a primitive root for mod PK. Okay, so from the fact that you know every prime have a primitive root, you can infer that all the prime power have primitive root. Okay or not? So far. Okay. Okay, actually this proof is actually quite interesting, but then we won't do it a bit long. Okay, so let's see. What should we do next? 1225. A lot of statement here. If you don't prove, it sounds a bit like an instruction book. So you basically, I just tell you what happened. You go and apply it. Because if you can study this proof, right, you can know why it works like that, and then you can see how the number get break up. Okay, but then these proof actually some of them are quite long actually, so you need some time to digest. Okay, otherwise it's very super dry. Okay, we'll see how it goes. So okay, before we go to next result, maybe we do some examples again. Okay, so let's do some examples. So does 4 has a primitive root? And then the second question is does 8 has a primitive root? Okay. So basically this is 2 to the square, right? And then the other one is 2 to the cube. Okay. So there's two questions here. Well, we can quickly use our strategy just now to do it. Okay. Let me see. Did I miss out any condition or not? I think I missed out some condition. So because this example is trying to bring out something special here. Okay, so this example here come with an odd prime. Sorry, even prime. Okay, but then maybe often people will forget about the condition here. This theorem work for odd prime. Okay, so when does this odd prime thing comes in? So at least this stage we need odd prime. Okay, so let's go back one step back. Yeah, do we need odd prime for the p minus 1 and p square minus p? So there's no odd prime here, huh? I guess there's no odd prime here. Let's go back a bit further. Any odd prime condition? Oh, here got an odd prime condition. Huh? This statement has an odd prime condition. Okay, this p minus 1 and p square minus p has an odd prime condition here. Okay, so odd prime condition will appear here also. Okay. So meaning this whole chain here only work for odd prime. Okay. So now we want to try and show you something about even prime. Okay, because this is 2 to somehow. Okay. There's really only one special case here only. There's no other even prime, because even number have to has divisor 2. Yeah. Because 2 here only has 2 and 1 as divisor, so it's a different case. Special case. Okay, so let's look at this special case here. So if we follow this strategy, right? Well, we can see that maybe 2 has a primitive root. Yeah, so what's that primitive root here? Which is 1. Okay, because 1, 2, 5, 1 is 1. Okay. So this is not an odd prime, so you cannot use the p minus 1 or r plus p business here. Okay. Okay, but then what? So you can ask whether 1 is a primitive root of 4 or not. Okay, 1 is a primitive root of 4. Obviously it's not because order of 1 is always 1. Okay, so then how to solve then? Okay, but obviously 1 is not. Oh. But then how to solve? Okay, how to solve here? So you can try the strategy just now, right? R plus P, because R plus P doesn't have the odd prime condition, so you can try that. So note that 3 equals to 1 plus 3, 1 plus 2 is a primitive root of 4. Okay. Not 4. Okay, so I mean you just check it. Sanity check. Since 3 to the 1, 3 to the 2, and then 3 to the 3 to the 3. Yeah. Is it 5? Wait, let me think. So what's 5, 4? 5, 4 is 5, 2 times 5, 2. Is it? 4 is 2 square minus 2, right? So it's 2. Okay, so just check about check 2. 3 cube, 3 square. So this is 3 mod 4. And then the next one is 9 mod 4, which is 1 mod 4. So 3 is a primitive root mod 4. How about next one? Okay. So this R plus P strategy works, huh? How about next one? Every odd prime would have a primitive root for all powers, but how about 2 cube? Okay, how about 2 cube here? So 2 square have, how about 2 cube? So what do we do here? Basically, we just do it very originally. So if you look at 5 of 8, which is 4, then you look for all those number that has GCD 1 with 8, right? Okay, and then you check their order. They're very natural method. Okay, but then what do you see here? Okay, but then you are very quickly you can compute that 1 is 1 mod 8 already returned to 1, 3 square already returned to 1, and then 5 square also returned to 1, and then 7 square also returned to 1. Okay, so meaning what? So they actually have order less than or equals to 2, okay, which is strictly less than 4. Okay, so there's no primitive root of 8. There's no primitive root of 8. Okay, is it straightforward? Okay, so I give you an example that there's some integer that doesn't have primitive root. Okay, and then I show you that every odd prime has a primitive root. Power of odd prime also have primitive root. Okay, or power of 4. But this number here don't have primitive root. Can we give a description to integer that doesn't have primitive root? Not sure. Let's see how it goes. Okay, next theorem. Okay, so this is the next theorem. So if I have an odd integer a, and the power k here is greater or equals to 3, then what we can show you is if you take a to the 5 of 2k divided by 2, or which means it's just a to the 2k minus 2, is already congruent to 1 mod 2k. Okay, what does this shows you? This shows you that if you consider number like 8, 16, 32, okay, 2 to the k greater than 3, then any odd number here, okay, any odd number here will return to 1 before 5 of 2k. Does it make sense or not? Okay. So implies that the order of a mod 20k should be less than or equals to 5 of 2k over 2, which is strictly less than 5 of 2k. So meaning it cannot be your primitive root. Okay, for all the odd integer. Even integer, you don't even need to think about, right? Because even integer is not relatively prime to the k. Okay, so meaning what? So meaning that 2 to the k greater than 3 wouldn't have a primitive root. Okay, would not have, because they will return 1 much earlier than 5 of 2. 5 of 2k divided by 2 already. Does it make sense? Okay. Let me see. Yeah. Okay, so the corollary here is 2 to the for the power for the integer that's written in the 2 to the k form has primitive root if and only if k is equals to 1 or 2. This is only the 2 possibility you can get primitive root. For the rest, it will get to 1 very quick. Okay, very quick in the sense that it's a half of 5 of 2k. Is it okay for you that we don't discuss about even integer here? Because they are not a candidate for primitive root. Because for even integer, you will have GCD and not GCD. But then you will have common divisor 2. So they are not a candidate for primitive root. Okay, so for it to be a primitive root, you must be at least odd 2. Not divisible by 2. It's also very interesting, but it uses induction. Yeah. Okay, so far so good. Actually, you can see this result here, right? So here was 2 to the 3 minus 2, which is 2 to the 1. Okay, so that's why you see all their power when raised to 2, it is 1. You see that? Okay. 2 to the 3 minus 2. Yeah, is 2. Okay, so when you raise all these odd integer to 2, you get 1. Okay. Yeah. Yeah, any question so far? Okay. All right. Yeah, next. So next is this. Okay. So very special this theorem here. Are we going to use this in any way? Let me see. Shall we use it? Not sure. Why are we looking at this one? But very interesting is you can show that the order of 5 Okay, mod 2k is 2 to the k minus 2. So 2 to the k minus 2, how do you compare to 5 of 2k? Okay, so 5 of 2k is 2k minus 2k minus 1. Is that right? This right? Is this right? Okay, and then 2k, if you put it up, okay, actually you just only can put 2k minus 1. And then you get 2 minus 1 here, which is 2k minus 1. Okay, so it's some number that's strictly less than 2k minus 1, which is 5 to the 2. Not sure why they deal with this 5. Are we using it later? Seems like no. But this proof is again very interesting. Yeah. But it uses induction, so no need to show you. Okay. So if we don't show you proof, there's a lot of statement that you need to convince yourself. If in any case, if you encounter any assignment that need proof that you think that I don't cover in class, please let me know. And then maybe I can tell you a bit more on them. And in case I miss it, I don't know. In case I miss it. Yeah. If you think that, hey, this one, like, Seng never teach before. So please feel free, come and talk to me. Don't come and talk to me after the due date, okay? I cannot help you. Don't come talk to me after you read the assignment and then you see that, oh, this method, like, I never teach before, like Seng never teach before. Then you can ask me before the due date, so that I can tell you a bit more. Okay or not? Yeah. Yeah, we try to keep this course as computational as possible because we need to consider people from different courses, right? Different degree. Okay, let's go a bit further before we finish today's lecture. So next theorem is if n is a positive integer that is not a prime power or twice a prime power, then n does not have a primitive root. Wow, this theorem is kind of very strong. If n is a positive integer that's not a prime power, okay, or a twice of a prime power, then does not have a primitive root. What kind of number looks like this? Do you have any idea? What kind of number look like this? Not a prime or twice a prime power. What number look like this? Huh? 6. Okay. So n equals 6. Okay, 6 is what? 2 times 3. Okay. So twice a prime power. Is this twice a prime power? It's not. This one is a prime power, right? 2 times 3, twice a prime power. Isn't it? This is 2 times 3 to the 1. The 6 has a primitive root or not? Want to try? Check. Huh? People want to try and check? So well, let's quickly check. Quickly check, verify this. So 5 of 6 is what? 5, 2, and 5, 3, right? 5, 2, 5, 3, which is 2. Okay, 2 is very quick to check. Okay, so good. So if any one of them is square to 1, then you found the primitive root already. So 1 obviously is not right. 2, 2 square is 4. So 4 obviously is -2 mod 6. 3, 3 squared is 9, which is 3 plus 6. 4, 4, 16, which is 4, 6. 5, 25, which is, sorry, 1, huh? Okay. So this guy is a primitive root actually. Okay, so because this is not a prime power definitely, but this is twice a prime power. Okay, yeah. So can you give me another number? This one has a primitive. Can you give me another number? Not a prime power and not a twice a prime power. Huh? Cannot think of it. Is it that hard? 20. Okay, let's try 20. So 20 is 2 to the square times 5, right? Okay. So is it a prime power? No, because you got a mix of prime power. Is it a twice of a prime power? So maybe you can pull this 2 out first. And then it's 2 times 5 a prime power. No, no, right? Okay, it's a mix of prime powers. Okay, maybe 20 works. You can go back and check. Is it true that it doesn't have a primitive root? Okay, I think this one works. Okay, this doesn't have prime power. Okay. Sorry, doesn't have a primitive root. Okay, so try and check that 20 has no primitive. Okay, so next, let P be an odd prime and R be a primitive root mod P to the K. If R is odd, then R is also a primitive root modulo 2 times P to the K. If R is even, then R plus P to the K is a primitive root of mod 2 times PK. So this means what? So you see where is our starting point? Previously, we know that we can found primitive root for P to the K. But now we extend it a little bit further. Consider 2 times PK, twice PK. Okay. So in this sense that we know that for every odd prime P, we can find a primitive root mod PK. Then now we can find one for 2 times PK as well. Okay. So you see the strategy is kind of similar, huh? But then this will be classified using R. Okay. If R is odd, then R is a primitive root. If R is even, go and plus the PK into it, and it will become a primitive root for mod 2 times. Okay, does it make sense? Right? Previously, we adjust using the order, right? But now we just look at whether the parity of R is odd or even. Okay. Yeah. Okay, maybe we can go and finish it. So the next theorem is, so a positive integer n has a primitive root if and only if the following things happen. Either n is 2, either n is 4. These are special case because they are not odd prime or they are not power of odd prime. Then C is only when power of odd prime you have primitive root. The other one is 2 times the power of prime. That's it. Okay. These are all the cases. Okay. For the other integer, you cannot find primitive root. Okay. So here is even prime. And then this one is power of even prime. And then this one is power of prime. And then the last one is twice power of twice prime power. That's it. Okay. For the rest, you cannot find primitive root. Okay. Yeah. Kind of restrictive, actually. Yeah. Any question before we finish? Yeah, kind of restrictive. Only 2 for P to T and then 2 times P to T. You can find this kind of primitive root phenomenon. Any question before we finish? Okay, if no, we will see you on Wednesday. Yes, see you on Wednesday.
Sure, correct.